All right, so here's another problem from Chapter 15, Mastering Chemistry. This one is called Interactive Worked Example 1512, and it gives you the reaction between hydrogen sulfide, showing it decomposing into hydrogen gas and sulfur gas. It gives you the K value and the initial values. So you know this is an ice table problem because it does not give you equilibrium values. It asks you to find the equilibrium concentration of sulfur. So let me show you my work on this. All right, so as always, I set up my ice table. I put the balanced reaction above the ice table. I filled in the all the information that the problem gave you, and so it told you the initial concentration of hydrogen sulfide and hydrogen. Well, actually the initial concentration of sulfur too. And as always, for the change row, you have to pay attention to the coefficients in the balanced reaction. And so since there's a 2 in front of hydrogen sulfide, it is going to change in increments of 2x. We have a minus sign because the reactants typically decrease in concentration. There's a 2 in front of hydrogen gas, so that is +2 since it's a product and they typically build up. And sulfur only has a 1, coefficient of 1 is assumed in front of it, so that's +x. Then you just carry out the math of each and get the equilibrium concentrations of each substance. So then you want to come down and write out the expression for the equilibrium constant. And I always suggest doing this generic expression instead of going straight to plugging in equilibrium quantities because it's so common for students to leave off exponents. And if you go back to the balanced reaction, you can see that there are 2 hydrogen sulfides and 2 hydrogen gases. So 2 of our concentrations are squared. So anyway, plugging in the equilibrium values we found from the ice table, we have this. Now, deciding whether or not to neglect x, you have to look at the value for K. K is, which is given, 1.67 times 10 to the minus 7, is several orders of magnitude smaller than the original concentration of what we're adding or subtracting x from. And the rule of thumb is if this K value is at least 3 orders of magnitude less than the initial concentration, you're safe. And this is 6 orders of magnitude left. So I'm going to go ahead and neglect x when it's added or subtracted to a number. And so what we end up with then is a greatly simplified expression. And when we rearrange that to solve for x, we get that, there it is. X actually equals the equilibrium constant, which is kind of weird. 1.67 times 10 to the minus 7. That is the concentration of sulfur gas at equilibrium. And your numbers might be slightly different, mastering chemistry, so be careful, but this is the general process by which it's worked.